Tonight's presentation is by Dr. Jared Nelson. Dr. Nelson is an assistant professor in the Department of Sustainable Product Design and Innovation here at Keene State. He's finishing out what is a very unusual first year for anyone in any institution. And he has a BS in philosophy from Bates College, a BS and an MS in mechanical engineering from the University of Utah, and a PhD in mechanical engineering from Montana State University. He's taught at the college level here and elsewhere. He's worked in industry, consulted for business, and been a writer and an engineer in his consulting work. His classes at Keene State include product design principles, 3D CAD, principles of materials, properties of materials, and product design for manufacturing. His research is concerned with understanding the effects of processing on material performance in natural fibers, composites, and 3D printed polymers. In his research, he's looked at industrial hemp, wind turbine blades, and textiles. And his talk tonight expands on this, and it's titled Natural Fibers as Sustainable Material Alternatives for Engineered and Industrial Uses. With that, I'm going to hand it over to Dr. Nelson and return at the end to help with questions and to close us out. So with that, welcome, Dr. Nelson.
Thank you. I appreciate it. I don't think part of me doesn't feel old enough to have done so many different things, but all of them have had unique challenges and been fun along the way. So okay, so here, bear with me for just a second while I figure out. There we go. Okay, so are you seeing just the single slide? Is that correct?
That's right.
Okay, I want to make sure I'm not showing you my presenter view with all my notes in it. So I'm pretty excited to be here today. This is it's I had a stint there where I was giving a talk in this arena pretty regularly, and with the past year being what it is. I realized, kind of pulling together my notes and going back and looking at this this slide deck, I've talked through this multiple times, but it's been over a year since I've actually had the opportunity to do so. And I think the last time that I had the chance to go through and talk about this in a format like this was last year when I came here and interviewed at Keene. So a number of things have changed a little bit, and I've realized a number of those changes ahead of time. I'm positive I'm going to come across a few things that I may talk around a little differently as we go through. One of them will be readily apparent when we get to one of the first few slides here. So again, natural fibers as a sustainable material alternative for engineered industrial uses. My background comes from composite materials. And I know I should not be leaving the screen, but this is one of the things that I work in. This is a carbon fiber bike frame, right? This is an area of expertise for me. I've worked in this industry since about 1997. Carbon fiber is great, except for the fact that it uses a petroleum product as a precursor to make it, except for the fact that it takes significant amounts of energy to make, except for the fact that it's really expensive, except for the fact that it's not recyclable, et cetera, et cetera. I think we see where I'm going with that. So a few years ago, I had the opportunity to start looking at natural fibers as alternatives for things like fiberglass and carbon fiber. And so that brings us to the talk where we'll go through today. So just by way of kind of getting us going and letting you know what's coming, I'm going to talk about different materials and the opportunity. Talk about processing to performance, industries, and applications. I have a few slides on that toward the front, and depending on time, we can look at some more individual cases toward the end. Again, if depending on questions and area of interest, that sort of thing. And then what I really want to talk about is engineering to assess variation. This is the portion where I am focused with my research. I think this is one of the keys to the industry. And we'll look at an approach that we have developed as a case study to look at using natural fibers, bamboo specifically, as an alternative for fiberglass. And then we'll move into areas of potential and growth and kind of and what's needed to really help this industry grow and take off. Again, this is at the heart of this. We hear about sustainability all over the place. We look at the UN has sustainable goals, development goals that are meant to develop the world in sustainable ways. We look at sustainability directly here on campus. It's one of our college-wide learning outcomes. And so just to, again, to kind of orient ourselves so that we're all thinking about this in the same fashion, we are looking at sustainability as the nexus of economic success, environmental prosperity, and social advancement. If any of those three legs are missing, we're not sustainable. We're in perhaps a good spot, but not a sustainable spot. Wrong way, Jared. So if we consider what is a sustainable platform, and what sustainable platforms exist, and perhaps more than anything, why we need sustainable platforms, we can look at some of these statistics. The ones that jump out are the two in the middle in white. We're using 3.5, or we're generating 3.5 times more waste in the US than we did 50 years ago. 3.5 times. That is a huge amount of waste. 91% of plastic is not recycled. There's a great talk a few weeks ago about recycling. Found that really interesting. And so it's, this statistic speaks to how little material is being recycled. However, on the positive side, 74% of companies say they're prioritizing direct supply chain to address sustainability, right? They want to achieve that nexus through their supply chain in some way, shape, or form. In other words, they're looking to improve. They're looking to strengthen that supply chain. If we look at the UN Sustainable Goals and Sustainable Development Goals, excuse me, they anticipate that we will see $12 trillion globally by 2030 in savings and revenue. So what's the big issue here? We have these sustainable materials, but the problem is the suppliers are unreliable. The materials are expensive and they lack, there's a lack of technical expertise. So this is, driven, we see long lead times for these materials. They're hard to get. The cost is high because the processing is high, which we'll get into in just a minute. The quality is inconsistent, and that is one of the major gateways for large industry. That first image showed, it showed a combine and then it showed a Tesla, right? In order to get into automotive, quality has to be very consistent. We can't have the ups and downs and the variability that we're seeing. And then likewise, there's limited availability of these materials. So I've had the opportunity to work with a company called Sunstrand. It's in and of itself is an interesting case of sustainability. And I will admit right now, Sunstrand is no longer a company. But we did some neat stuff, and we really pushed forward kind of the envelope and really centered around a sustainable competitive advantage. And so we started, it actually was a group of engineers that started the company, one lead engineer, and then several of us engineers supporting him. And we started from a very engineered perspective. Typically, if you look at hemp and natural fibers, it doesn't start at that point. It starts from a farmer, for example, who says, okay, I have all this material, what am I going to do with it? And so then they say, well, if I process it, then I can sell it to these various industries. We figured, okay, if we can figure out what are the specifications needed for these materials, then we can try to engineer these materials and figure out how to how to grow them, but then how to process them, further refine them and convert them. All along through this processing, refine, and convert, all of these are opportunities for revenue, right? So we can sell materials at any point along this process, depending on what the end use need is going to be. Okay, so I've made it this far and I haven't really talked about the material yet. So the materials that we're looking at are things that typically they are what we call bast fiber plants. A bast fiber plant, we'll see a cross section of it in just a moment, but it's typically grown. It regenerates quickly. It's flax, it's hemp, kenaf, things like that, that can be grown in the season. In fact, some areas can see multiple growing seasons in a particular year. And there are, if you're at all familiar, the material itself is not analogous to hay, but there are a lot of similarities in how it is grown and the approaches to growing it to hay. I don't want to draw that analogy other than to say there are similarities. So what we do is we grow the material. That is a huge amount of science that I'm really not going to get into at all tonight. But so the outcome is we get this material that ends up being a baled product, as we can see here, that then goes into some sort of processing facility and is then processed into fiber and core. So we can see that basically this plant has a fibrous outside and this woody core on the inside. This is called the bast fiber on the outside from the bast stalk. And that is generally the highly sought after material. That's the material I'm generally talking about when I say we're looking at replacements for things like fiberglass and perhaps carbon fiber. We also have this inner material, this inner woody core, that can be used in many other products. And we'll get into some of those. Oh, let's get into some of those right now. So this is what the stalk looks like after the plant is harvested. All we've done here is we've taken it and we've sliced it right down the middle. And so we can see the bast fibers on the outside, and we can see this inner woody portion here that supports the plant as it grows up. And it's this outer fiber that really gives the plant its strength. The bast fiber themselves are sought after for textiles. Patagonia has been using them, as have other apparel companies. Also for technical textiles, for cordage, netting, canvas, rope. Hemp rope is one of the things that rope is one of the most commonly thought of things when we start to talk about hemp. And then we can also look at technical textiles for geotextiles, biocomposites, things along those lines. This inner woody core can be made into fiberboard insulation. It's used in a material called hempcrete, which is a replacement for concrete. And then also it has perhaps the biggest growth we've seen is animal bedding products, as well as chemical absorbents. It's also used to grow mushrooms. There's a company over in outside of Albany, New York, that came up with a technology to grow mycelia in particular ways for food packaging. And so hemp, this hemp hurd is the material that they use to grow that mycelia from. And then the whole stalk can be used in other materials. So there are a lot of uses for these materials. Likewise, when we put these materials into use, we get some really nice benefits from an engineering perspective. We get good vibration damping, we get good water and oil absorption, we get significant weight reduction. This is a big one, and we're going to come back to this in a few minutes. We get significant weight reduction because these materials are much lighter than the materials that they are replacing. And so this is perhaps one of the biggest, from an engineered perspective, one of the biggest wins that these types of materials can see. We can see cost reductions, acoustic insulation, filtration media, thermal insulation. So you can see a lot of absorption, a lot of insulation directions here. And then likewise, we're seeing that these are being utilized in animal care, paper and pulp. We can generate and create plastics from these materials. We can make building materials, textiles, and the automotive industry is really kind of that, I think, that next step that once quality can be achieved, then these materials will find use in that industry. And there have been some trials to this point. So looking at some specifics, these are some example engagements that we had with Sunstrand. So VF Corporation is a clothing corporation that owns Wrangler, Lee, North Face, and some others as well. They're kind of a big deal. And so they're a worldwide company, apparel company, and we worked with them to develop a hemp fiber specifically to go into denim jeans and jackets to basically strengthen those pieces of apparel. One of the things they wanted to achieve is, or one of the targets they were looking at was workwear. One of the downsides we see to these materials to this point is the processing hasn't been clearly defined all the way through. We'll talk about this a little bit more as we go. As we process more and more, we start to see a degradation in the material response and the material properties. So they're trying to kind of toe this middle ground of getting a consistent material. Unfortunately, that material doesn't always feel great against the skin in an apparel situation. However, in cases of things like workwear, where you want that additional toughness, it can be a real benefit. So another engagement was with a company called Retech. They are a leading producer of reinforced polypropylenes, primarily for automotive. And in this particular case, we took a polypropylene thermoplastic that had a 20% glass fill and upped it to 30% hemp, and basically reduced costs and improved or kept all of the key metrics the same. So the weight dropped, right? The density reduced because hemp weighs half as much as glass. It weighs less than the polypropylene. And oh, by the way, we bumped it up by 10% compared to the glass. So this product got significantly lighter. It was significantly less expensive. Again, because the hemp itself was hemp filler itself was less expensive than the glass or the polypropylene. We saw an increase in the impact resistance, the stiffness, and the heat deflection remained similar. So again, thinking about this from the approach that Sunstrand took in this, sustainable competitive advantage, one of the things as I mentioned, one of the things we really focused on was this engineering. And notice it says we were focused on understanding the market and assessing needs, right? One of the key areas that is missing in this industry is actually connecting this compatibility across the stakeholders. So basically, one of the things we realized pretty early on, and this is one of the reasons between us, this is one of the reasons why Sunstrand didn't quite make it, is what I'm going to talk about next was not available yet. What was missing was a good understanding of how to use these materials, a good understanding of the characteristic material properties associated with these materials, how to trace the agronomic variables. So for example, I said we weren't going to talk at all about how this stuff is grown. Well, you could have the same field, you could plant it in the same way, you could use the same seed 2 years in a row, but you can't predict the weather. You can't predict what's going to happen after you harvest this material and you leave it in the field and you ret it, which, that's a process by which then bacteria come in and separate that bast fiber from that herd material. Those things aren't really as controllable as we would like. And so therefore, we have to trace and be able to understand how differences impact the end fiber. Furthermore, there's no standardized testing or reporting procedures. This then kicks up to manufacturing compatibility. It makes, makes these things of upstream manufacturing processes, identification of material properties by manufacturing process, and further characterization for material compatibility. That's that next level. We need to know all of this level 1 stuff before we can do understand this manufacturing compatibility, which furthermore gets complicated when we actually want to apply it to an end use. So typically, if I were, as an engineer or a designer, going to go and specify a fiberglass, for example, I would know these first 2 levels, and I would know an awful lot about this 3rd level already, so that I could basically perform any analyses that I needed to to then do a competitive analysis to see if this is a material that I wanted to use. Looking at this in a slightly different way, what we determined was having this materials database was critical. And so that would allow us to tie together from farm to processor to use, how we can basically grow the materials, how we can sort them, how we, what particular fibers are useful for composites versus garments versus technical nonwovens. Similarly, what the particulates that we're getting out, where are those useful in composites and fertility and absorbance, as well as other material options. Because again, we want to take every single bit of this plant and we want to find a revenue stream for it, right? That's one of the key components to this being sustainable. And so that entire point of processing along the way is critical to that end use. So to help us visualize that, if we consider if this is the hemp stalk that I was showing a few minutes ago that was sliced right down the middle, we can then start to break it down. And so we have a process to do that, whereby we call it decortication. And so we decorticate the fibers away from the hurd. So the fibers are the green portion here, and the hurd, the woody core, is the orange section in the middle. And so basically what we can do is we continue to process the hurd down to smaller and smaller pieces, smaller and smaller bits, to get to really, really fine particles that have an array of uses. Similarly, we can get through and we can fiber open and basically pull these apart and get to different fiber sources, or excuse me, different fiber sizes that again can be utilized and sourced in different ways by different industries. I want to point out that while this is a neat image, and we think of this in kind of this nice, clean, everything is happening in this nice fashion, what we can see in reality is we have this, this fiber here, which is probably in this refined, it's been opened and has been treated in some fashion. It's not that clean. It's not a nice, round, uniform fiber like we would see from a carbon fiber or fiberglass. And so that's one of the things that makes it difficult. Again, just to give some background and kind of in some of the different types of plant materials that are available, flax, hemp, jute, all the way through to cotton. And cotton is really listed here as a comparator. And so we call these plant materials lignocellulosics. And that's because they're primarily made of cellulose and lignin materials. They have some other additives, which generally, as we go through, we kind of want to take those away as we move and process. And we really want to get down to the cellulosic fiber. That's what's shown here on this side. And if we can get down to that, that's the piece in this that really holds the strength. It has the stiffness. It has the material properties that we want to achieve and we want to realize in engineered technical applications. And so we can go through and we can look at how these different materials compare in terms of those different components and constituents that make them up. We can then get into and look at the material variations. This is a slightly different set of materials, but we can see cotton here, flax, and hemp. And one of the things, really the key takeaway from this is the variation. Notice the variation. Density is pretty consistent, right? Density is listed as a single number. However, fiber length is a range. Hemp goes all the way from 5 millimeters to 55 millimeters. That's a factor of 11. That's a huge variation. Similarly, our diameter ranges from 10 microns to 51 microns. A factor of 5, again, a huge variation. We see our elongation at break varies by a factor of 3, and our tensile strength by a factor of 2. The takeaway from this is that with variations like that, it is really hard to be able to specify a specific material for a specific end use. You can ask students in my in the properties of materials class. We're just talking about it today. We're talking about predicting when a material is going to fail, when it's going to reach this elongation at break or tensile strength end. In order to do that, we need to predict a single number, at least a small range, not factors of 2, 3, 5, 11, things along those lines. So some of the things that contribute to those wide ranges are different characteristics and defects that we see. So this is a nice, consistent, uniform fiber that my research group took a while ago when we were looking at specific defects and trying to identify. We then identified fraying where we have microfibrils, and you can see these microfibrils peeling away along the length. And so we get variations in thickness. We basically get these little branches coming off, which don't really have much load carrying capability and make the fiber itself really kind of, material properties get thrown off by those. We can see we have a kink here where we have a sharp corner or change in direction. And then we have just general inconsistency where we have changes in variation along the way. Not to mention, I mentioned these constituents. We can break them down and we can do chemistry to determine them in the way that they did in those charts. But we want to know it in situ. We want to know it as these materials sit, ready to go as they come out of processing. How much lignin is there? How much cellulose is there? What is the constituents? What are the constituents of these materials? And so we can look at this SEM image that we took a while ago, and we can see that we think we've identified cellulose here. We think that we've identified lignin here. But how can we go back and forth and really try to analyze what is the difference between these things and how much of each one exists? So we did some further microscopy work where we were able to basically identify the lignin and the cellulose that existed in these fibers. And so basically we were able to do a volumetric study of this image and determine that based on the wavelength of light that is coming off of this, we can do an analysis and determine basically how much of this image is green and how much of it is not in this fiber area. Based on that, we can calculate the percent of the green, which we associate with the lignin. And so that's particularly useful where we can see we have pockets of lignin in this other image. So that's the direction we're going in my research. So to really start to dive into the research itself, here are some of the key things that we know. We know that natural fibers are inherently variable. We know they're difficult to characterize for some of the reasons we talked about. The constituents are hard to follow. The processing is inconsistent. There's so many variables going into this equation that it's difficult to pull all these things together and understand all these variables. They're difficult to bond to. If we could get rid of all of that lignin, we can get rid of all the waxes and pectins and everything else that are on the surface of these fibers. It becomes significantly easier to bond to these surfaces. They are highly process dependent as well. And because of all these things, because of all this variation, they're really difficult to use and design and to specify for end use. So really there's an opportunity here, right? And that opportunity is to basically tackle all this and say, okay, we can optimize natural fiber testing standards and take these standards and develop an accessible database of material properties. That's that database that was at the heart of that image that I showed a few minutes ago, right? This then allows business collaborators to assess and validate manufacturing compatibility for industrial applications. If we can start to pull together some of those data that I mentioned, that I can go easily find if I want to specify a steel or an aluminum or a fiberglass or anything along those lines, if we can start to build a database of those materials, then we can start to actually realize use of these materials in these industrial applications. So my group is working in this direction. I have two students working with me right now, Ben and Ryan. we're in the process, as much as anything right now, of trying to get the lab set up and get these pieces of equipment up and going. These two pieces of equipment are critical to the research we're doing. And so what we are doing is we are taking a bundle of fibers and we are extracting them down. It's a little hard to see in this image, but we can see it more clearly here. This is the fiber, this is the fiber that we're testing right here, okay? And it's really a bundle of fibers. Going back to those images that I showed, those SEM images, we can see that we have small bundles of cellulose fibers, but we call these individual hemp fibers. And so we are testing these bundles of cellulose fibers that are held together by this lignin. And so we have two main steps. We use two main pieces of equipment to do this. The first is this fiber dimensional analysis system, and I'm going to click on this and hope that this plays. Oh, there we go. Nice. I hope that's playing. And so what we can see is that we have a fiber in here, and we have a laser that is projected across here. The fiber blocks out some of the light from that laser. As it spins, we can get a diametral analysis. So we can measure what is the diameter through all 360 degrees of that fiber. What we end up with is a curve at each point along this length, as we see in this graph here. We can then use these diameter data to then help us, once we've tested this material, to be able to calculate stress and strain. The beauty of that is, if we only capture load, we're able to basically make statements about a particular fiber. If we capture load and we're able to convert it to stress using cross-sectional area, then we can make it a material property. If you want to learn more about that, come take properties of materials with me. We can talk about that for an entire semester. So again, this is a key piece of equipment because it gives us that cross-sectional area information that then allows us, when we place that same fiber into this linear extensometer and then pull it in tension and break it, we can then convert the data that we're getting from that to stress and strain. And we can do that as shown in this, this figure here. This is a stress strain curve for a particular fiber, and this is calculating the stress utilizing different cross-sectional areas depending on what we see here. And so it can vary significantly, from that point. So again, considering what we are seeing for cases such as, the VF case, that allows us to determine the strength properties of the fibers going into that case. We can determine the material properties, again, of the hemp fill that is going into this retech case. So I just want to bring this up again. But really, what's really interesting is if we do a comparison to glass. This is a really nice case that we developed a number of years ago, and it actually involves bamboo. And I like talking about this case because a lot of times I get pigeonholed into being characterized as a hemp researcher. I'm not a hemp researcher. I'm a fiber researcher. I research fibrous materials, and that includes carbon fiber in other portions of my research. This comparison between fiberglass and bamboo is, I think, a pretty compelling case, and it really emphasizes why we're doing the work that we're doing. Straight off the bat, this is a stress strain curve that compares our glass fiber to our bamboo fiber. Two key things to take away from this. We can look at the endpoint here of the bamboo, and we can see that we're failing at about 1,000 MPa. That's all well and good. What's an MPa? Doesn't really matter for us at this particular time. Comparatively, we can look at a glass fiber, and that's failing at roughly 3,000 MPa. So there's a factor of 3 difference in this strength. We can also see that our strain at failure is just over 2 and just over 4. So basically, the fiberglass is stronger, and basically it stretches more before it breaks. If we start to, so if we look at that off the cuff, we think, why even consider bamboo? Well, again, let's come back to that weight issue, right? One of the key factors I mentioned early on was regarding weight, and we can see, we know that the natural fibers are about half the weight of fiberglass. So if we look at specific properties, in other words, we divide our our stress and our strain by density, all of a sudden we're looking at a much more competitive product, right? The stiffness, in other words, the slope of the lines are still different. The bamboo is not nearly as stiff as the fiberglass, but we can see that we're getting a lot closer in terms of the strain at failure, and we're getting much closer in terms of the strength, the stress at failure. So we're seeing some benefits when we consider weight. Now, if we then go ahead and say, okay, if we're looking at an opportunity that utilizes 15% glass as a volume fraction, right? So 15% of this chunk of material is fiberglass. Well, one of the ways that we can go ahead and actually see a benefit and bamboo can be competitive is if we actually increase that fiber volume fraction to 30% for the bamboo. And so in that case, we can see that if we compare the 15% case, basically we can, our modulus of elasticity, in order for that to be the same, we have to bump up to just over a 20% volume fraction from fiberglass. Sorry, let me slow down for a second. I get excited about this stuff. If we have 15% glass fill, we can get a similar stiffness response by bumping it up to a 20% bamboo fiber fill. Similarly, if we look at a 30% glass fill, we can get a similar modulus of elasticity by bumping it up to just over 40%. These are attainable numbers. These are not unrealistic values that we can achieve. So we can see, just by bumping up the volume fraction, we can reduce the amount of plastic that goes into these materials, and we can achieve the same stiffness. If we go ahead and do a similar analysis that looks at the composite density, we can also see that with these same analogies, we're seeing, even though we're increasing the amount of fiber, we are dropping weight. We are less dense by increasing and going to bamboo at this increased level in both cases. Pretty significantly, we can see that our composite density goes from about almost 1.4 down to just under 1.2, and similarly from about 1.6 down to 1.2, and that's grams per cubic centimeter. So again, we are achieving similar stiffness and we're dropping weight significantly. So then, with that increased volume fraction, we can now start to see that we also, as a composite material, are starting to get really competitive. We can see that these two lines between our bamboo fiber composite and our glass fiber composite are nearly identical up to this point. So we can see that basically the glass fiber is still going to be a little bit stronger, and it's still going to have a little bit more deflection, or still have a bit more deflection or deformation before it fails. But generally speaking, we've attained a close comparison to these materials, or by substituting bamboo in, we've attained a similar material response. And so that's, this was when the light bulb went off for us, that there was something here. And so really thinking about this and really thinking, okay, there are multiple knobs that we can turn here and we can engineer to get to these end uses that really are compelling and realistic. And so with that, I'm going to take a few minutes and I'm going to shift gears just a little bit and start to look at some existing products before I move on to taking some questions. So there are generally different classes of end use. The easiest one that we can attain and doesn't really need a whole lot from that case study that I just showed are consumer goods, right? I think we're starting to see bamboo toothbrushes. In fact, my daughter just got one when she went to the dentist a couple of weeks ago. She came home with this bamboo toothbrush. So things like that, coffee mugs where the this outer shell is replaced with a hemp-filled material or a fiber filled material, as well as within 3D printed plastics. Another opportunity we can see that's kind of, again, lower hanging fruit. We're kind of, as I go through here, we're kind of moving up in technical capabilities and technical merit, let's say. So kind of low hanging fruit is fiber batt insulation and a CoreBoard type material. So these are alternative building materials where we get similar performance, similar R values from this insulation, similar performance to typical plywood from this plywood material. This is an interesting case that that was achieved by Lexus. There are numerous cases. BMW has a few, Ford has a few. They've all been pretty short-lived and kind of done on a trial basis. But this is a rear seat board in this Lexus RX. And we can see that it's, this is the actual seat board itself. We can get an idea of the thickness. This is a bamboo pen, by the way. So another consumer good use. And so we can see it's pretty thin material. And so it's basically meant to add some stiffness and some other damping properties and so forth in the back here. It's a 50% polypropylene, 50% hemp material. Yeah. One of the most exciting areas, I think, is, it's really not that exciting. It just shows what a dork I am. One of the most exciting areas is the what we call the tub and shower market, or the boat market. It's the spray up market. Spray up composites are nasty. They use awful chemicals, and so I won't get into that. But there are alternatives that are coming onto the market that allow for the fiberglass to be replaced in this chopper gun. So it's a continuous fed natural fiber that's fed in through this system shown in the back. And then we can have bioresins that are sprayed in through this system as well to then go into tubs, showers, kind of low engineered or less engineered composite materials. And then we can get into the super high end. This really gets into that highly refined end that I was showing earlier. The nanocellulose, the graphene, super absorbents, functional additives, things along those lines that that really need further definition and further characterization to be realized. And it's interesting. Some of these things are taking off, and the science behind them is compelling. And some of these will become products before some of that lower hanging fruit that I just mentioned. So again, really kind of hitting on these performance attributes. We can see things like absorption for water and oil, acoustical and vibration damping, thermal insulation, filtration, aesthetics, things along those lines. And so really at the heart of my research has been this idea of this Bioindustrial Materials Institute. And so that is really kind of, again, it goes to that idea of that opportunity that I shared to use collaboration to develop comprehensive understandings of these materials and their opportunities to increase their competitive and use. And so with that, I am happy to take any questions.
Good. That was really terrific. Really nice slides. Really, I have some questions.
Awesome.
But I'd like to throw it open to other people first to ask their questions. Making sure that I've unmuted myself and that I'm viewing correctly and things. Okay, so so there's one, Warren. He's asking, do sunflowers have usable bast stalks? Thinking about other materials.
I don't know. That's a good question. I'll find out. I've never been asked that, and I've never considered it. Um, my gut tells me no, but I really don't know.
So that gets to one of my questions, okay? And that is that hemp is, you talked about bamboo, you talked about hemp, now we're talking about sunflowers and flax and things like that. There's various biomaterials, that you grow, harvest, and attempt to employ in uses such as these. But one of the things that you said in your talk also was that, I'm not necessarily, I don't necessarily want to be classified as another hemp researcher.
Right.
And I kind of get a feeling for why that might be. And I think that, to my perception, especially after your talk, it seems that hemp research has gotten much more mainstream and much less associated with the stigma of marijuana and things like that, or being seen as sort of a stalking horse for bringing that into a
And that
legalization.
stigma has significantly reduced as well. I mean, that stigma has significantly changed over the past 5 to 10 years.
And that's my question. So you've seen it go from sort of an outlier to a very normal discussion in circles?
It's a much more normal discussion. That's a really good question. It's, you know, if you go back 5 to 10 years and before, the hemp industry and the cannabis industry is essentially one, right? And then states with the, geez, I apologize, 2014 is when the laws changed, and basically it became up to individual states to mandate how they wanted to approach legalizing hemp and marijuana. And that's why we see the current wave of cannabis legislation that we've seen. So many states became partners with the DEA and basically came up with hemp research programs. That at the time, that was the key step to starting to move in the direction of making cannabis legal. Is the approach that many states took. What that allowed them to do basically was determine research partners, start to allow those partners to grow hemp. And so farmers could become a research partner with an institution as long as it was regulated by the state, and as long as that state had passed hemp legislation, they could then go ahead and do that. Since then, the hemp industry has started to migrate away from the marijuana industry. The two are kind of starting to extract themselves from one another. Interestingly enough, the materials that I'm working with have never been illegal for hemp or marijuana. You go back to the initial legislation, and there's a clear exception for marijuana stock, the stock material and the hemp stock material. The reason I don't want to be associated as being a hemp researcher is because I want to be seen as being a hemp researcher, a flax researcher, a kenaf researcher, a glass fiber researcher, a carbon fiber researcher. I want to be seen as a composites researcher. I want to be seen as a fiber guy. You know what I mean? And so I don't want to just be seen as only focusing on hemp because there's so many other opportunities, and because so many people are focused on hemp, that's all they hear. And so I like to make that distinction, Mike, that the research I'm doing goes well beyond just hemp.
Sure. And I really got the impression that, hemp is among the array, and it has
Exactly.
qualities that recommend it, and some qualities that are problematic, like the diverse characteristics on breaking and strength and things like that.
Yep. Absolutely.
And which brings me to another question. I'm just going to hog questions here, but I was an engineer a long time ago, and I had a professor who was a materials guy, and he did reinforced concrete, and he tested it for strength, and he just basically tried to get as much uniformity in in his test pieces and then just sheared them and pulled them apart and crushed them again and again and again until he got confident that he was pretty clear when they were going to break. Is that what you're doing with the pieces that I see between the two ends?
Yeah, that's a really good analogy, Mike. I think that we're not even to the point where we can understand things like there's so many unknowns that go into it. So at this point, yes, we're trying to do that, but the gentleman that you're referring to, there was decades, if not centuries, of research prior to him in this arena. We're kind of jumping into this and trying to draw as many analogies as we can. But we don't know our ass from our elbow at this point. So we got to jump in somewhere and really try to understand and gather as much information as we can. So I like to think about this as though we don't really know everything that we're testing for, but we're trying to watch everything that happens and trying to catalog everything that happens so that as things happen, we can start to draw these analogies and start to learn what's our elbow, and start to develop that characterization.
Good. How many times does it take to pull apart a stock before you develop some confidence about the strength of a material?
It takes a lot. So right now I mentioned I have two students working with me, Ryan and Ben. And we generally work in batches of 20 fibers. And so what that entails is a rather monotonous process of taking material that's sent to us from a partner. We've been working with a school, SUNY Morrisville. There's a researcher there. She's a fiber, a plant scientist. And basically, she's sending us her fiber. We then take, and she sends us little bits of the fiber from various points in the stock and other things that we're looking at. And so it's a few ounces of material. We can get hundreds of tests out of that, but we're testing right now in batches of 20 in hopes of getting, 15 to 18 good tests out of that batch. And so then we can start to get some statistical, meaning out of it. But really it comes down to, again, we're still trying to figure out what are all the keys that go into it. As we extract, it takes longer to get smaller fibers, and it takes more care to get smaller fibers. And more than likely, as we get smaller fibers, we're probably adding more damage to those fibers as well. So they're going to appear to be weaker. And so figuring out what's that, kind of right area to say, okay, this is the size fiber that I want to test and get a meaningful test out of it is a key component.
Good, thanks. I've asked two questions. Is there anybody else that would like to jump in? I see some faces on the gallery.
I can ask a question.
Yes.
Oh, so my question is, Jared, so are you thinking any kind of matrix, like you want to add that kind of reinforcement, or you are just characterizing the fiber at this point?
Yeah, that's always on the horizon. Great question, Dr. Habib. Thank you. So these materials, at least in one of the avenues that I've been talking about, and the avenue that I have great interest in, is composites, right? And so composite material has those at least two constituents. We look at carbon fiber, and I used to have a phone case that I would hold up in these situations, but I got a new phone and it didn't fit anymore. And so that phone case was carbon fiber. Carbon fiber is the fiber that is reinforcing the plastic matrix material. And so there are matrix materials that are available, but compatibility is an issue. Bonding to the natural fibers is a significant issue. And Dr. Habib and I have a mutual colleague who's done a lot of really good work in this area to develop resins and develop matrix materials from natural sources that are compatible and work well with these materials. So that tends to be, the resin itself, the matrix itself is not an area that I'm directly focused in, but that is a key consideration in the next steps of this research that I'm doing. One of the next pieces of technology that I want to build or figure out how to do is to basically replace one end of the test that I was doing where I was pulling on the fiber, replace one end and be able to put a droplet of resin on that one end and then have the fiber come out of the other end. And then we can pull on the fiber and hold the resin and we can see how strong is that bond between those two pieces. And that's, I think that's, that's going to be a key next step going forward.
And I can just add a little bit. I saw like some researches where people were trying to modify the surface by using maybe some chemicals or some, that can be another option. Just I'm pretty sure you are considering that thing.
Absolutely, that's in that big ball of processing. That there are some things that I know a lot about in that big ball of processing, and there are some things that I don't know much about.
Yeah.
That surface functionalization is an area that's has amazing opportunities, but I don't know much about it. I'm not a good chemist.
So, well, there's a question in the Q&A about naturally grown materials being used in industrial processes. It says, can naturally grown materials be raised, gathered under reasonable quality control to be competitive with glass or carbon fiber, or are there too many variables in natural fibers? This is really interesting, I think. Yeah,
that's the key question. My intuition says yes, and it's not going to be, so if we're saying, using the example of glass that you used in the question, it's not going to be an all or nothing, right? And what I mean by that is there are situations where glass is going to perform better and outperform these materials, and these types of materials will have too much variability to be realized in certain situations. Cases that automotive has used so far are kind of low-hanging fruit where they need key things. They need vibration damping. They need some structure, but it's not a structural component. So for example, BMW did a headliner a few years ago. Maybe it was Ford. Now that I'm saying that, it was BMW or Ford did a headliner a number of years ago, and that headliner needs to have certain structural characteristics, but it's not replacing the frame, right? Sorry, I feel like I'm kind of talking myself in a circle here. What I'm trying to say is that it's not a panacea, right? It's not going to be everything. Hemp fiber is not going to replace all of fiberglass uses. There are some where it can be a good alternative, and those are the ones that I think need to be targeted first. And it's the development of those that can allow us to then see where other opportunities exist as we build from those opportunities. Does that make sense?
Yes, and it's really interesting, and it's something I'd never thought about until tonight's talk, that variability and the challenges. Couple other questions in the Q&A. There's a question that goes from Warren. Because hemp isn't as strong as fiberglass, could it be used for controlled compressibility?
Probably. I don't know that that's something. Yeah, I don't see why not. It's going to be determined. There are a number of factors that would also go into that, environmental considerations and so forth. But it's not something that I've seen considered yet. Let me put it that way.
What can I ask? What controlled? And maybe Warren, you could jump in. You seem to know. What is controlled compressibility? Or Maybe Warren's
I'm going to
not.
tell what I think it is, and
Okay,
if
good.
Warren wants to jump in as well, I more than welcome him to do so. What I'm interpreting as he's asking is, based on a particular application of load, this material would compress certain amounts to known values. And, is that, could we use this material to help control that?
Yeah, to control deceleration. In other words, if if you have a very stiff material, deceleration would be instantaneous, which would be bad for the human element. But if you were to have a material that would, it has to be consistent, like you say, but because it's not as strong in certain aspects, it could be used, with similar processes, but just a different fiber to have a controlled deceleration to help survivability in accidents and things like that in the automotive industry, because that's what we're talking about.
Gotcha. Yeah. Okay. So I'm going to change my answer just a little bit then. Thanks for clarifying, Warren. It's a great topic. And we can catch up more on it for sure.
Sure.
The composites in general, the anisotropy of them, in other words, the different properties going in different directions, really allow themselves to be designed for things such as energy absorption, like you're talking about here. Changing fiber direction, I think, is going to be a bigger factor than changing what type of fiber it is. So, for example, back in my earlier days, I worked on a project. We developed and manufactured a carbon fiber hood for General Motors, for Corvette. Pretty neat project. And it was the first time that a carbon fiber panel had been used and gone directly into an automotive facility and then used as original equipment. One of the benefits to that carbon fiber hood that we did not realize when we designed it was that by having the fibers basically run crossways generally, in other words, there were no fibers running fore aft on the hood, it performed significantly better than the previous glass fiber hood did in crash tests, right? So front impact, basically that carbon fiber hood, carbon fiber is twice as stiff as glass, right? Significantly stiff.
Yep.
And so it absorbed, I think it was 30 to 40% more energy than the previous hood did. So I think it would be a consideration, Warren.
Yeah,
for sure,
that's
but
what I was kind of thinking. If you have a structure and it's like, okay, I want this part to be somewhat absorbent, we'll just throw in a little bit of natural fiber, and if the process can remain the same for the whole system, just it's good for this part of it, because you don't get the ultimate strength, but it reacts the same as the rest, so it will seem like the rest of it, but it'll be like like there's certain airframes that are designed to crash, but once you crash it, then it's over.
It's done, right?
Yeah. So, but it's designed to save life,
right?
So that
exactly,
you may be damaging your component, but you don't reduce the overall strength of it. But the part that is vulnerable, something like that. Yeah.
Yeah.
I'm talking in circles. I'm done.
Yeah, no, it's
This is really interesting, and actually I'm super glad that you got on the microphone, Warren, because it's really interesting to hear the kind of detailed conversation that can happen, and it makes sense. It's just something
it's kind of hard to do it in a few words.
Sure. Sure. So I'm gonna see if there's other questions. I don't see any, and that's fine because we're right about on time. But there's one observation I want to make before we sign off, and that is, what a difference, between this talk and some of the other talks that we've talked about, the Hollywood blacklist, we've talked about medieval literature, we've talked about the white tendency in the environmental movement, we've talked about COVID employment trends, and it's been an amazing semester so far. And so the thing I wanted to point out is, aside from just how interesting it is to be able to do this, Students in the KSC 199 section, all of you who are here tonight, I'm really pleased to see that. If you find a way to tie all these talks together, or maybe say 8 of them instead of the 13, without talking about how different they all were, I'll give you extra points. That's a really interesting challenge, and it's been a really interesting thing that I've seen. And with that, I want to thank Jared for a really great talk, nice slides, cool research he's doing. If there's people out there that want to talk to him more, please look him up. If there's students that want to take his class, please do so. And so thank you, Jared. And
my pleasure. Thank you. Appreciate the opportunity.
Oh, it's great. We'll see you guys next week if you join us, and we've got 3 more. And good night until then.